Okay. So my work it's about a novel solution to multi-group neutron diffusion equation by Hankel transform formalism. Let me just okay. So the principal idea here is of this work. This work is for me and my classmate Renato Klein, one of my students, a great student, and I will to start this work. I need to make a brief list introduction about nuclear problems, and so we need to start with nuclear fission. For example, it's of course that we know, but we need to remember briefly that nuclear fission works like a neutron. It's inside a source element and uranium, and after this we have the nuclear fission by two new elements that we call fission product 1 and 2, and this process has energy liberation, and of course this process have radiation emission too. So our work it's about calculate the neutron fluxes inside this problem. In other words, calculate the neutron flux inside nuclear reactor. The nuclear reactor it works, and we call this and we work with the nucleus of the nuclear reactor. And if we take a top view about the nuclear reactor, we can see something like this. For example, a lot of different regions, different elements, and different things about and the core of the reactor. In this work, we use to radial symmetry, and the radial symmetry we can see that works when we take a top view like this one. And of course, in these problems, we take a lot of, for example, modeling, and here we take a diffusion equation like a model, but it's normal. We take transport equation or diffusion equation of this problem. So here we take a diffusion equation that is approximating of transport equation that is well used in these problems of nuclear reactors, and we need to explain a little bit more to use diffusion equation for multi-group equations. So the idea here first is change the Laplace operator. For example, if we use the cylindrical symmetry, and in cylindrical symmetry this operator is like this one, and we need to change. So it's normal, and each one of these contents here, for example, phi is scalar neutron flux. It's the more important. It's that we need to know. We have d like a diffusion coefficient. We have sigma r remotion cross section, sigma f fission cross section, ek effective critical coefficient. Our problem is to solve for the phi, for scalar neutron flux. So we have the simple diffusion equation in steady state. We have do not depend of the time here, and to understand this a little bit better, we need to understand what is the multi-group neutron equation. For example, we have level of energy or different levels of energy in neutrons, and if we take a just simple example, we have, for example, this range, a big range that is, for example, from 0 to 0.025 electron volts. We call neutrons. The next range is from 0.025 from 0.4 electron volts, the thermal neutrons, and this one, and this one. We have a lot of types or a lot of kinds of range in neutrons, and our problem here is a simplified problem. For example, if we take only two ranges, in other words, we can simplify and change this for neutron, thermal neutrons, and fast neutrons. And of course, we have a more big range because we have only two groups, and we call that group 1 and group 2. Group 1 for fast neutrons and group 2 for thermal neutrons. I need to say that this work only works with two neutrons groups, but we can extend this problem for more group neutrons. So, for example, here The equations can be changed a little bit. We have a multi-group system diffusion equation, that is the first one equation, and that is the second one. These equations is so similar, but a little bit different. For example, we have the diffusion coefficients for each group, we have flux, the phi1 and phi2 for each group, and cross-sections for each group. For example, removal cross-sections, we have fission cross-sections, and we have two more elements and two more, in other words, two new elements, sigma 1, 2 and sigma 2, 1 in the last term of each equation. Sigma 2, 1 is the scattering from the group 1 from the group 2, and sigma 2, 1 is scattering from the group 2 to the group 1. In other words, we have a range of energy for each group, and this range of energy can be changed in the system. So because of this, we need to consider these new two terms, and they put this in our equation, and our system of equation that's coupled, and we can solve this using two kinds of methods, in other words. So this system of equations can be replaced like this, and here we need to say that Ni is the average number of neutrons per fission. We compute like 2.5, for example. And this system of equations, if we open a little bit more, open the summatory, and of course using some algebra here, we can show that this is open equations, these two equations, and we need to know that here we just put the new source terms. For example, we consider the first term in the right hand side on the first equation like a source for the group 1, and the second term from the right hand side like a source for the group 2. So the idea here is just change this and put source in the point. Now we have a system of equations, of course, but non-homogeneous systems. We have two new sources, source 1 and source 2, represented by S1 and S2, respectively. And we have two conditions, basically. The neutron flux can be horizontal on the start from 0, and so the derivative term at 0 is 0. And the limit of the system, the capital R, is 0. We call this an extrapolate distance, that the flux is so small that we can consider 0. In other words, it's the same. And we have here two operators, the Laplace operators and cylindrical coordinates, and we need to pay attention with this. For example, the first method is using definite Hankel transform to solve this problem. And of course, definite Hankel transform have this inversion. That is the representation like this summatory. Of course, this the first one is an integral and the second one is a summatory, and both of them use the Bessel functions that sometimes is complicated to evaluate. But here we have a property, a special property. This special property is about these terms that involve Laplace operators. And if we apply the Hankel transform of order 0 in Laplace operator with the constants with this coefficient of diffusion, we have this expression, the last expression. And we need to remember that in this case we have the condition in the capital R is 0, the flux. But if this appears here, we need to change this property, like for this one. And of course, the term with the operator can be changed when we apply the Hankel transform. So we have here other representation for system of equations. For example, if we change or if we take the transform and transform system, we have the new equations. Of course, that here is not more in R, in Xi, it's a new variable, and the system is algebraic now. We can solve this one. It's really easy to understand this. And so this is a transform, this is a system that we can put in a matrix system like this one. And here we just call for new variables and new functions to have a more compact and visual matrix. Of course, here we have a matrix and we have the new fluxes, like as a vector for solution, and we have a vector for the source. This method can be extended, of course, for more than 2 groups. I just show here for 2 groups because it's more simple to understand. So this matrix system can be solved if we pay attention that for determinant of this matrix is like this one, and of course we need to solve this problem, and we need to understand that if we calculated the inverse matrix and just putting the right terms on the right place, we have a new solution. We have the expression for a solution in the space transform. It's not the first space, is the solution for C, not for R. So now we need to remember that to take the solution or the final solution, we need to come back and we need to apply the finite Hankel transform inversion. So to apply this is relatively simple. We need to just apply the summatory and the Bessel functions for the transform functions, and we have a solution like this. That it's a final solution, for example, for the system in the matrix form, and we can call this and the final solution using finite Hankel transform. So we can call FHT solution to use the more compact notation. So that's a solution for our problem. But we can ask, what happens if we use the infinite integral Hankel transform formalism? In other words, if we use the formalism using the infinite domain, what happens? We can solve, or we not can solve. What happens if you take the another method? So just to remember, the infinite Hankel transform is by definition this one, and infinite Hankel transform inversion is this one, just to remember. And here we have the same property for that Laplace operator. That is good because if we remember, the system is the same when we apply the conditions and apply the Hankel transform. We have the same multi-group system diffusion equation like this one, and we have the same algebraic solution in transformer space. But now, if we need to make the inversion, this is different because it's not summatory. Here we have another integral. So what we have here, what's the problem now? The infinite Hankel transform inversion is like this one, and if we apply the inverse transform in here, we have the different formulation, not more summatory. We have integral, and here is the flux 1 and flux 2. But these two integrals is not easy to evaluate. It's not too easy to evaluate, not for phi1, not only for phi2, and we need some other method or other procedure here. What we do here. So, for example, this methodology, these two integrals can be extended like this one, and here I will take some algebraic modifications, just putting in blue the new functions that represent the terms in that matrix system, and here we consider just flux 1 to show the methodology. Of course, that's analog for flux 2, but I'm going to consider just flux 1. And we need to call two theorems. The first one is the Hankel inverse theorem. That say that if we have the new variable c times f and times j, that is a Bessel function for order gamma, for example, like this one, and we have the Parseval relation that represents for two different functions, f and g, for example, this relation. So this relation of the Parseval relation it's very nice to solve this problem if we can apply this both theorems in this case. What happens now? So the conditions of these two theorems are satisfying here, and we need to apply this theorem, the Parseval relation, to understand what we have and what we can reach here to solve this problem. So I will show the method right now. For example, if we take just the first one, integral. Of course, for the second one, integral, for the second term, it's analog, but I will show for the first one. And we have this term to solve. That is very complicated because it involves a Bessel function of order 0, involves a determinant that is not too easy to compute too. It involves a source that here is not null, the source. Of course, for the simulations, I will put a source, but here, not yet. So we consider the two functions, f and g. Of course, that's two functions in the space transform because we not invert yet, and I need to solve this integral. And applying the Parseval relation, we have that this is equal to that second integral. For example, the g is the source one, and by the Parseval relation is just the source one in the first space. So the source one depends on r. Xi is the r, it's equal. And the problem is that inverted this box equations, a2 times j0 by determinant of m. That's the new problem here. So if we need to invert this problem or invert this equation using the Parseval relation, we need to remember that the new form, that's new form here, that we need to invert, we can rewrite, of course, by the definition of inversion of Hankel transform. That is that one. And if we pay attention for some terms here, for example, a2 by determinant of m, we can rewrite this form. Here I just use the definition of determinant. And if we make some algebra here, we can rewrite again like this one. And here we have some interesting thing. For example, the second one, 1 by 1 minus p1 versus p2, there are constant, by a1 plus a2. That's a really interesting thing here. For example, we can extend this or expand this like this one. For example, if we take this one, this representation, that just works if we have that term, it's less than 1, absolutely less than 1. And indeed, this term is so much less than 1. We have some simulations from the pattern of this term in the space transform, and we have this result, for example, and that show that is satisfying. So we can expand this in this way. It's really simple idea, and because these terms are really small, we can consider here just one term. In other words, just the first term. And if we consider this approximation, of course that is approximation, it's not exactly, we can rewrite the integral like this one, and the function a1 we have by the definition, and we can change right now like this one. And here we have to we can rewrite this problem. For example, if we take some algebra here again and again, and just here I just call alpha 1 from sigma r1 by d1, and we can replace this in the integral, and of course take off the coefficient day1, and after make this the coefficient day1 take off for the integral. We have an integral really interesting, because this integral, it's a well-known integral, and we can rewrite this form where I0 and K0 are the modified Bessel functions of order 0, and the first order and the first functions, and after the second kind of Bessel functions. And here we take R prime, for example, between 0 and R, and after we have R prime between R and infinity, in other words, more than R, and we can replace this in the first term. And now for make the solution, or for express the solution, we can just put this in two integrals, or in other words, two integral system, and we have this one like the final representation. But the thing is that here we have two integrals that are so much simple to understand and to evaluate. The first integral, if you remember, it's not too easy to evaluate. And here we have two integrals that is more simple to evaluate. And that is represent the final solution. Of course, the particular solution, we need to make a homogeneous solution that I do not show here, but is easy to obtain. And we call that AHT solution in compact form, just to compare with the first one, FHE solution. So we have two solutions for the system. These two solutions, the first one FHE and the second one AHE, representing a solution for each fluxes, phi1 and phi2. Of course, in the screen have only phi1 for AHT solution, but we have the solution for phi2. And we need to compare. And we need to compare this with the results. So, just to show you the results, I will put here some nuclear parameters to show the results for us. And these parameters are basic nuclear parameters. Remember that the cross sections are the probabilistic numbers, so are the number from 0 to 1 at maximum. And we made the simulations for 4 sets of parameters, and we use here the set 2 just to show in that a normal situation. For example, if we take the flux 1 results, normalize it, we have from 1, of course, because it's normalized, and we use R, capital R, like 5 in the system, and we have some pattern of solution for the flux 1 using the set 2, of course. And here we can understand too what happens with the flux 2 or the phi 2, and we have the same normalization and the same domain, and we have different pattern. It's very similar, but it's not the same. And if we put this one together, we can see that it's not the same. It's have a little bit difference. Okay. And here we have, for example, some numerical solutions for the problem. The first one is FHE with 10 terms in the summatory. 10 terms in the summatory represents the 10 Bessel roots using to make these calculations. And the second one, we have 50 terms in the summatory. And the third one, we have 100 terms in the summatory. And EHT is the same solution, for example, because it's the closed solution for the problem that is approximating. The thing is that when you use less terms of the summatory, we have decimal places of accuracy small. For example, we have 1 decimal place of accuracy, and the second case we have 2 decimal place of accuracy, and the third one 4 decimal place accuracy. But the thing is that the IHT, the second one method, is not the exactly solution, but here represents make a better solution, because of course FHT is exact solution, but we need to take a lot of terms in the summatory. So these simulations are made in Python, and of course if we take more terms of summatory, the simulations can be a time computational time bigger. That can be not so good. We need to understand what is better for us, in other words. And here we show that the formalism for the Hankel transform is good, and we need to And we can, in other words, we can using the AHT like exactly solution or better than exactly solution FHT, taking a lot of terms of the summatory. So in the future works, we want to extend this word or this work for more than 2 groups, of course, and we need that. We believe that that's not so easy to make, but we believe that it's possible to extend for more than 2 groups, and the future works we need to take this possibility. And the formalism for the Hankel Trussman in cylindrical coordinates, showing a best idea and the best, in other words, showing for us that it's a good method to understand this problem. Of course, that we can solve these like numerical problems, for example, using a numerical method. But first one, we need to analyze and we need to take a idea, for analytical idea, that is this one. So that's all, folks. Thank you.